Hello class, welcome to Unit 7, Video 5. Today we're going to go ahead and look at polynomial functions. We've already been working with polynomials and doing synthetic and long division. But today we're going to evaluate polynomial functions using function notation. So just a reminder, you have done function notation before, but that is that f of x. And so maybe we'll ask, well, what is f of 2? That means you're going to plug 2 in. The other learning target is that I can identify general shapes of graphs of polynomial functions using the degree and the end behavior. Okay, so we're going to be looking at those things today. So a cross section of a honeycomb has a pattern with one hexagon surrounded by 6 more hexagons. Surrounding these is a third ring of 12 hexagons and so on. The total number of hexagons in a honeycomb can be modeled by the function f of r, where r is the number of rings and f of r is the number of hexagons. It says find the number of hexagons when r equals 4 and r equals 3. Okay, so r is the number of rings, f of r is the number of hexagons. So what we need to do is plug in 4, so we need to find f of 4. That means there are 4 rings. So we have 3 times 4 squared minus 3 times 4 plus 1. So, following order of operations, exponents first. So I have 3 times 16 minus 3 times 4 plus 1. Then there's no other parentheses really because it's just showing multiplication. So we multiply and divide from left to right. So 3 times 16 is 48 minus 12 plus 1. And then we add and subtract from left to right. So 48 minus 12 plus 1 leaves us with 37. So f of 4 is equal to 37. So this means that when there are 4 rings, there are 37 hexagons. Okay, let's go ahead and do the same thing and let's find f of 12. So when there's 12 rings, so f of 12 will equal, plugging in a 12 wherever there's an r. Notice how this 12 is in the spot of this r, so I'm going to put it in for all the r's here. So it's 3 times 12 squared minus 3 times 12 plus 1. So 12 squared is 144 minus 3 times 12 is 36. 3 times 144 gives me 432 minus 36 plus 1 equals 432 minus 36 plus 1 gives me 397. So my answer is f of 12. When there's 12 rings, there's 397 hexagons. So that's a little bit of function notation. So today we're going to look at polynomials in one variable. Okay, so in order to be a polynomial, this is what has to happen. It can only have one variable in the polynomial, and you cannot have variables in the denominator of a fraction, okay, or negative exponents. So to be a polynomial, you can only have one variable. No x and y involved, just x or just y. And then you cannot have any variables in the denominator. The next thing we're going to talk about is the degree of a polynomial. That's the largest exponent of the monomial. So largest degree, largest exponent. So the degree is the largest exponent. And lastly, leading coefficient, that has to do with the degree. It is the coefficient of the term with the greatest degree. So it is the number in front of the variable with the highest exponent. So we'll look at some examples of this. So it says state the degree and leading coefficient of each polynomial in one variable. If it is not a polynomial in one variable, explain why. Okay, well, to be a polynomial in one variable, there can only be one variable. So looking at example 1, there is only one variable, and I cannot have any variables in the denominator. No fractions here, so we are set. So the degree is the highest exponent. Okay, well, this is x to the first, this is really x to the 0, so I have 0, 1, 2, and 4, so the degree is 4. Then my leading coefficient is, if my highest degree is x to the 4th, it's the number in front, so my leading coefficient is 7. All right, number 2. First of all, is it a polynomial in one variable? I have x, I have xy, and I have y. There's not one variable, there's two, so that means it's not a polynomial. It has two variables. All right, and number 3, we have x to the 6th, x to the 3rd, and 1 over x. So I only have x's, so I have one variable. However, I have a variable in the denominator. So once again, that means it's not a polynomial. And the reason is there's a variable in the denominator. Got a little crowded, but in the denominator. Okay. Moving on to example 4, it says find the following values given the polynomial functions. Okay, so this one says find f of b squared. Notice how the b squared is in the spot of our x. So wherever there is an x, I now need to write b squared. So to find f of b squared, it's going to be equal to 2, now x, so b squared, to the 2nd, plus 3 times b squared minus 1. And then we would simplify. So I still have 2, b squared to the 2nd. So remember, I multiply those. So 2 times 2 is 4, so it's b to the 4th. Plus, there's nothing extra, so 3b squared minus 1. So here is f of b squared. Okay. 5 says find 2 times g of c plus 2. So I'm really going to take 2 times g of c plus 2. In order to do that, you probably have more room on yours, but I'm going to write it down here. So we would have 2 times g of c plus 2. So notice g of x. So wherever there's an x, I'm now going to put a c plus 2. So right here. So I have 2. I'm going to put a bracket because it's 2 times all of it. 2 times, I plug in here, c plus 2 squared minus 4. I need to simplify what's on the inside. Biggest thing that people think is you can just distribute the 2. You cannot. You need to FOIL it. So let's write it out. We would really have c plus 2 times c plus 2 minus 4. This will equal 2 times, if I FOIL this, c times c is c squared plus 2c plus 2c plus 4. Then don't forget to write the minus 4. Combining my like terms, I can add those. So I have 2c squared plus 4c. 4 minus 4 is 0. So there's that. And the last thing I need to do is to distribute the 2. So I have 2c squared plus 8c. So that is my answer for number 5. Okay. So now we're going to go ahead and look at the graphs of polynomial functions by using their degrees. Okay. The first thing that we want to know is just looking at this. This is a 0 degree, so this is our constant function. If we have something to the first degree, that's a linear. So y equals mx plus b, this is really to the first power, so it's a first degree. Anything to the second degree is a quadratic. ax squared plus bx plus c. The third degree, all third degrees look like this. Fourth degree, okay, looks like this. And here's fifth degree. So let's first of all take a look at even degree problems, or even degrees. Notice the shape of it, okay? And here's another even degree. What do you notice about the endpoints? You should notice that they're going the same direction. So when you have an even degree, ends go in the same direction. Okay? Either they both go up or they both go down. So that's one way you know if it's even or odd. If they're both going up or both going down, it is even. If they're going in different directions, so if you went ahead and took a look at this one is an odd number, one's going down and one's going up. Once again, one's going down, the other one's going up, and the same thing with my fifth degree. So odd, and I would make sure you write this down on your notes, ends go in different directions. Okay, something to take note of. If I ever want to find the degree and I don't straight up tell you, it says the hint, count the number of times it changes directions. Okay, well, a change in direction, if I look at this one, I'm going down and then I'm going up. So here, wherever there's a curve, that's a change in direction. So how many changes in directions do I have here? I have one. So changes in direction. There is one. Okay, how many changes in directions are there here? 1, 2. How many changes in direction here? 1, 2, 3. 1, 2, 3, 4. Anybody see anything that would help me figure out my degree? Well, if you count your changes in direction and you add 1, you'll get the degree, which is, for this one, 2. So I would do this, plus 1 gives me my degree of 3. 3 plus 1 is 4. 4 plus 1 is 5. So if you ever get asked to find the degree, you count your changes in direction and add 1. Okay. Let's go ahead and look at the end behavior of a polynomial. Okay. So the end behavior is the trend of f of x as x approaches negative infinity and positive infinity. All right, so maybe just let's look at it. What do negative infinity and positive infinity mean? If I'm looking at a graph, and the trend of f of x, we're looking at what y happens as x goes to negative infinity. So this is my x-axis. If I head in this direction, I'm going to negative answers. So this is going to negative infinity. If I head to the right, I'm going to positive, so it's going to positive infinity. So what we're doing is we're looking at what happens to the y values, or f of x, as x approaches negative infinity, which is to the left, or positive infinity, which is as we look to the right. Okay. So we say, what does f of x do as x approaches negative infinity, and what does f of x do as x approaches infinity? So we'll look at some examples like this coming up. So here's just some more information. If the degree is even, okay, that means I am, if you look at this one, both my ends are going in the same direction, so I know it's going to be even. And then to figure out what the degree is, I would say, well, there's one turn in direction, 1 plus 1 is 2. So I know it's an x to the second. If I am opening upward, we know that my leading coefficient is positive. And we have went over this in previous chapters. So for this one, if a is positive or greater than 0, we know it looks like this. If a is less than 0, we know it looks like this. Same thing happens here. We know our leading coefficient is positive if we open up. We know it is negative if we are opening down. Okay. Same thing happens with our odd functions. Okay. If you look at this one, as I read from left to right, I am increasing, so that means I am positive. If I look from left to right, I am going down, which is negative. Okay, so that's how I know that's negative. The other thing that we need to talk about is end behavior. This is what we just got done talking about on the piece above. Okay, so we would say as x goes to negative infinity, f of x, what's happening to our f of x values? So looking at this one, negative infinity. So that means we're looking to the left. What's happening to my y values? They're going up and up and up, and they're going to keep going up and up and up forever. So they're going to infinity. Then let's look at it as we go to the right. As x goes to infinity, what's happening to our y values again? So now I'm looking to, as x goes to infinity, this is my x-axis going to the right. What's happening to my y values? They're going to keep going up and up and up again, so they are going to infinity. So this is my end behavior, okay? Look at the next one. As x goes to, once again, negative infinity, what happens to my y values? So as we go to negative infinity, my y values are going down, and they're going to keep going down and down and down, so they're going to negative infinity. And our other one is as x goes to the right, or as x goes to infinity, what's happening to our f of x values? So we go to the right, my y values are going up and up and up, so it's going to infinity. This is a big concept that you guys will see over and over again. So if you're struggling with end behavior, please come and ask. Especially as you go through math, you're going to want to understand it. Okay, the next two. Maybe write down the end behaviors on your own. So if you want to deposit, that would be a great idea. This one, as x goes to negative infinity, as we look to the left, what's happening to my y values? So as I look to the left, my y values are going down, so they're going to negative infinity. Now I'm going to look to the right. As x goes to the right, or positive infinity, my y values are going down again, so f of x goes to negative infinity. Last one to look at here. So as x goes to negative infinity, so to the left, my y values are going up and up and up, so f of x goes to infinity. And as x goes to positive infinity, as I look to the right, my y values are going down, so f of x is going to negative infinity. So this is all end behavior for each one of those graphs, because you're going to be asked to do end behavior today, so you want to make sure you understand that. The other thing we need to talk about is domain, remember, is your x values, and range is your y values. If you're an even degree or an odd polynomial, notice that the domain will always be all reals. What that means is I'm going to go all the way to the left and all the way to the right, okay? Because these arrows are going to continue on. Your range is your y values. So looking here, will I ever turn around and go here? No, these are going upward. So my lowest one is, for this case, it'd be y is greater than or equal to, what's my lowest y value? 0. If you're an odd, notice I'm going to go all the way down and all the way up. So my range is all reals. Same thing here. My domain, all the way to the left, all the way to the right, but my range, it's not all values. I'm not going to get the positive. So it's y is less than or equal to my y value, 0. Lower than 0, so going negative. And once again, this one is going to go all the way to the left and all the way to the right. That's my domain. And range, it's going to continue all the way up and continue all the way down, so that is all reals. Okay, so there isn't a lot to write here, but there is a lot of information here. So I really hope you wrote down some of this stuff, because it's going to come in handy. All right, so we have 3 more examples to do. Okay, so it says for each graph, describe the end behavior, determine whether it represents an odd degree or even degree polynomial function, and state the number of real zeros. All right, so the first thing let's do is say if it's even or odd. Number 6, I notice both arrows are going down, so if they're going in the same direction, I know it is even. What would the degree for this one be? Remember, number of turns plus 1. So there's 1, 2, 3 turns. 3 plus 1 is 4. So it's an even degree of 4. All right, the next thing is end behavior. So as x goes to negative infinity, f of x goes to, so as I look to the left, what's happening to my y values? Going down, so it's going to negative infinity. And as x goes to infinity, my f of x values are going to, well, as I go to the right, my y values are still going down, so negative infinity. The last thing I need to do is state the number of real zeros. Those are your solutions, your roots, your x-intercepts. So how many x-intercepts do I have? 1, 2. So I have 2 real zeros. Okay, so that is number 6. Number 7. I look at this one. Once again, both my arrows are going in the same direction, which tells me it's an even degree. To figure out the actual degree, I would count the number of turns plus 1. So there's 1 turn, 1 plus 1 is 2. Then I would look at my end behavior. As x goes to negative infinity, as I look to the left, my f of x values or my y values are going up. So going to infinity. All right, and the next one is x goes to infinity. So now in this case, we're looking to the right. My y values are still going up, so f of x goes to infinity. Now how many zeros? How many x-intercepts? Well, I never touched the x-axis, so in this case, there are no real zeros. Okay. That is number 7. Number 8. Okay, first thing I notice is one arrow is going down and the other one is going up. That tells me it is an odd degree function. And my degree, number of turns plus 1. So 1 turn, 2, 3, 4. 4 plus 1 is 5. Okay, then the next thing I need to do is talk about my end behavior. I will say this. Sometimes they'll write it reverse. F of x approaches what as x approaches negative infinity, just so you see it both ways. So as x goes to negative infinity, as I go to the left, what happens to my y values? I'm going down, so to negative infinity. They just put in the opposite order. F of x approaches what as x approaches infinity? So now in this case, I'm going to the right, my y values are going up, so to infinity. There's my end behavior. And the last thing is, how many zeros do I have? I have 1, 2, 3, 4, and 5. So 5 real zeros for this one. Okay. That is it for Unit 7, Video 5. There's a lot of information here that you will see over and over again, so if you have questions, please let me know. Otherwise, have a great day, and I'll talk to you later.